Geometric Physics 1, Lecture 3, Covectors, Phase Space, and Exterior Forms. Today's reading is Frankel, sections 2.1 through 2.7, pages 37 to 81. For next time, read sections 2.8 through 2.10 and chapter 3. This is the lecture where phase space appears. Nearly everything later in the quarter rests on one object, which we meet about halfway through the hour. Last time we built the tangent space to m at P and the tangent bundle Tm. Those are the homes of velocity. Today we build the dual side. About halfway through the hour, one object appears. We call it theta, and in coordinates we write theta equals pi d qi summed over the index I. Theta is a one-form on T star q, the cotangent bundle. Theta is the most important object of this quarter. The route has 4 stops. First, covectors and y momentum is 1. Second, the cotangent bundle T star m and the tautological one form. Third, tensors, and then the antisymmetric tensors, which give us the exterior algebra. Fourth, the exterior derivative d and the pullback f star. Here is the one-line summary to carry through the hour. Vectors push forward, covectors pull back. Every asymmetry between the Lagrangian and the Hamiltonian pictures traces back to that one sentence. First, covectors. We take a vector space and look at the linear functions on it. Momentum is going to turn out to live there. Take a real vector space E. The dual space, written E star, is the space of all linear maps from E to the real numbers. That is the entire definition. A covector is a machine that eats a vector and returns a number linearly. Choose a basis E1 through En for E. That choice determines a dual basis for E star, written sigma 1 through sigma n. The rule is that sigma I applied to Ej is 1 when I equals j and 0 otherwise. That is the Kronecker delta. Write a vector as v equals viei and a covector as alpha equals alpha I sigma I. The pairing of alpha with v is alpha I vi summed over I. Now change the basis. The components of a vector transform with the inverse matrix, and we call that contravariant. The components of a covector transform with the matrix itself, and we call that covariant. Here is the point. The pairing alpha IVI does not change because the two laws are inverse to each other. That invariance is the reason for the up and down index convention. The convention is a bookkeeping device that makes coordinate independence visible at a glance. Take a smooth function f on M and a tangent vector v at P. A tangent vector is a directional derivative, so let v act on f. Define df at P, apply to v to be v of f. The result is linear in v, so df at P lives in the cotangent space at P. The differential of a function is a covector. In coordinates, df equals the partial derivative of f with respect to xi times dxi, and the dxi are dual to the coordinate vector fields. Notice what we did not use. No metric, no inner product, no length. The differential df needs no extra structure. The gradient is different because it needs a metric. Grad f is defined so that the inner product of grad f with v equals df applied to v for all v. In Cartesian coordinates on Rn, the two look identical. In other coordinates, they do not. Grad f picks up inverse metric factors g upper ij. So picture df as the level sets of f. Then df applied to v is the number of level sets v pierces. Nothing in that picture needs length or angle. A Riemannian metric on M assigns to each point P an inner product on the tangent space at P, varying smoothly with P. In coordinates, G equals Gij dxi tensor dxj with the matrix Gij symmetric and positive definite. A metric gives an isomorphism from the tangent space to the cotangent space, and an inverse going back. Feed a vector v into the metric and leave the second slot empty. The result is a covector written v flat. Feed a covector into the inverse metric, and you get alpha sharp. In components, v flat is Gij vj, and alpha sharp is G upper ij alpha j. Those are lowering and raising indices. So grad f is exactly df sharp. Now the idea to hold on to. Symplectic geometry supplies a different isomorphism from Tm to T star M, built from omega rather than from G. That isomorphism sends a vector v to the interior product of v with omega. The symplectic map is antisymmetric rather than symmetric, and it is not a metric. There is no notion of length in symplectic geometry. We proved that in Lecture 7. Hamiltonian mechanics needs only this one. Now the geometry. We collect all of the cotangent spaces into one manifold, and we find phase space sitting inside it. Now do for covectors what we did for vectors. T star M is the disjoint union of all the cotangent spaces, one for each point of M. The projection pi sends each covector back to the point it sits over. A chart on M induces a chart upstairs. A covector at P is recorded as the n coordinates x, followed by the n components alpha. That makes T star M a smooth manifold of dimension 2n. Now, why does momentum live here? Start with the Lagrangian L, a function of q and q dot on TQ. Define P sub I to be the partial derivative of L with respect to qi dot. Change configuration coordinates from q to q tilde. Velocities transform with the Jacobian of that change. Run the chain rule through the definition of P, and the Jacobian appears the other way up. The new P tilde I equals partial qj by partial q tilde I times pj. That is the covariant law. Momentum is not a velocity with different units. Momentum transforms the opposite way from velocity, and momentum lives in a different space. Hamiltonian mechanics is set on T star q for this reason and no other. Here is the object the quarter turns on. A point of T star q is a pair. A point q and q together with a covector alpha q sitting over q. A one-form on T star q must eat a tangent vector upstairs and return a number. So take v, a tangent vector at alpha q. We already own a covector. We are standing on one. But alpha q eats vectors on q, and v lives upstairs, so push v down. The tangent map T pi does exactly that. That is the definition. Theta at alpha q applied to v equals the pairing of alpha q with T pi of v. Push the vector down, then feed it to the covector you are standing on. Nothing was chosen. Not coordinates, not a metric, not even the manifold q. Every ingredient was there the moment we wrote T star q. In coordinates, write the q components of v as ai. Pushing down kills the p components, so theta of v equals piai. That is, theta equals pidqi. Finally, any one-form beta on q pulls theta back to beta itself, and theta is the unique one-form that does this. Now define omega to be minus d theta. In coordinates, omega equals dqi wedge dpi. Four things follow. First, omega is closed. That is, d omega equals 0, and we get it for free because d omega equals minus d of d theta, and d of d is always 0. Second, omega is non-degenerate. If the interior product of v with omega vanishes, then v is 0. Third, Hamilton's equations become one line. The interior product of xh with omega equals dh. Fourth, any map f from q to q lifts to a map T star f on T star q, and that lift preserves theta. Preserving theta forces preserving omega. So every point transformation is canonical. That is a theorem you were probably taught to verify by grinding through Poisson brackets. We prove all of this properly in lectures 7 and 8. Today's job is to earn the three symbols the statement is written in. Those are d, wedge, and f star. Now the sentence to keep. Omega equals 0 is not an assumption we impose. Omega equals 0 is a consequence of d being 0, together with the fact that omega came from the tautological theta. So we owe ourselves those symbols. We start general with tensors and then keep only the antisymmetric ones. A covariant K tensor at the point P is a multilinear map with K slots. Feed it K tangent vectors and it returns a number linearly in each slot separately. A contravariant K tensor is the same idea except that it eats K covectors. A mixed tensor of type Rs eats R covectors and S vectors. Components come from feeding in basis vectors. The components of Q are the values of Q on the coordinate vector fields. The transformation law then carries one Jacobian factor per index, all of them the covariant way up. You already know several tensors. The metric Gij is a covariant 2 tensor. The symplectic form omega ij is a covariant 2 tensor. A linear map is a mixed tensor of type 1,1. The inertia tensor of a rigid body is a covariant 2 tensor. One remark on culture: Frankel's phrase, a tensor is an object that transforms like a tensor, is the component definition. The multilinear map definition is the same statement with the quantifier moved. Physicists, index gymnastics, and mathematicians' functor talk are two dialects for one object. You should be able to speak both fluently by week 4. Now restrict attention. An exterior K-form is a covariant K-tensor that is alternating. Alternating means swapping any two arguments flips the sign. That one condition is enormously restrictive. The space of K-forms has dimension n, choose K. A basis is the wedge products dxi1 through dxik, with indices strictly increasing. Two consequences follow at once. There are no K-forms when K exceeds n. And in the top degree, when K equals n, the space is one-dimensional. The wedge product of a K-form alpha with an L-form beta is a K plus L form. Take the tensor product and anti-symmetrize. The wedge is associative and graded commutative. Alpha wedge beta equals -1 to the power K times L times beta wedge alpha. In particular, alpha wedge alpha is 0 whenever K is odd. One warning before you open another book. Two normalizations of the wedge are in common use, differing by binomial factors. Frankel uses the determinant convention, in which dx wedge dy applied to u and v equals u1v2 minus u2v1. Check the convention before quoting a formula from elsewhere. Factors of k factorial are the usual casualty. Let us get a picture, because forms are visualizable. A one-form is a family of parallel sheets with a density and a sign. Alpha applied to v counts how many sheets the arrow v crosses. A two-form is a family of tubes, or oriented two-dimensional cells. Beta applied to v and w counts how many cells the parallelogram spanned by v and w encloses. The count is signed. Swap v and w, the parallelogram flips, and that is the antisymmetry. An n-form on an n-manifold is a density. A top-degree form assigns a signed volume to each n-dimensional parallelepiped, and up to scale there is only one. Here is the payoff. On Rn, dx1, wedge through wedge dxn, applied to n vectors gives the determinant of the matrix of their components. The determinant is not an accident of linear algebra. The determinant is the unique top-degree form up to scale. Now the two operations that make forms worth having. One of them differentiates forms, and the other changes variables in them. Here is the theorem. There is exactly one family of linear maps D from K forms to K plus 1 forms with three properties. 1. On functions, df is the differential we defined earlier. 2. D is an antiderivation of alpha wedge beta equals d alpha wedge beta plus -1 to the degree of alpha times alpha wedge d beta. The sign is the price of moving d past alpha. 3 d of d is 0. Those three properties determine d completely. In coordinates, alpha is component functions times basis wedge products. Then d alpha is d of each component function, wedge onto the front. Why is d of d 0? Check on a function. Do of df is the second mixed partial derivative of f with respect to xj and xi times dxj wedge dxi. The coefficient is symmetric in I and j because mixed partials commute. The wedge is antisymmetric in I and j. Symmetric against antisymmetric gives 0. So here is the sentence to keep. Div d is 0 is Clairaut's theorem, wearing a hat. Everything downstream is that one fact. Curl of grad is 0. Div of curl is 0. Charge conservation, the Bianchi identity. On R3, this machinery collapses into vector calculus. Use the standard metric and orientation to identify 0 forms and 3 forms with functions, and 1 forms and 2 forms with vector fields. The degrees then line up with objects you already know. Degree 0 is a scalar field, and there d is grad. Degree 1 is a vector field, and there D is curl. The pattern continues. Degree 2 gives div, and degree 3 gives 0. So the chain from omega 0 up to omega 3 is exactly grad, then curl, then div. And d of d is 0 says two familiar things at once. Curl of grad is 0, and div of curl is 0. Now the catch, those identifications use the metric and the orientation. That is why vector calculus does not survive curvilinear coordinates without square root of g factors, and why the magnetic field B is really a pseudovector. Forms have no such problem. More on that in lecture 4. 2 words. A form alpha is closed if d alpha is 0. A form alpha is exact if alpha equals d beta for some beta. Since d of d is 0, every exact form is closed. The converse is true locally, but it can fail globally. That failure is where topology enters. Here is the standard example. Take the plane with the origin removed. On that space, let alpha be minus y dx plus x dy, all divided by x squared plus y squared. A short computation gives d alpha equals 0. Locally, alpha is d of the angle function. But integrate alpha once around the unit circle and you get 2 pi, not 0. If alpha were d of a globally defined function, that integral would have to vanish. So alpha is closed and not exact. There is no global angle function on the punctured plane. The failure of closed to imply exact is measured by de Rham cohomology, the kernel of D modulo the image of D. De Rham cohomology detects holes. That is the mechanism behind the Aharonov-Bohme effect, behind magnetic monopole quantization, and behind the topological charge of an instanton. We meet all three in lectures 25, 30, and 38. Let F be a smooth map from M to N, and let alpha be a K-form on N. The pullback F star alpha is a K-form on M. The recipe is forced. At a point P of M, we are handed K tangent vectors. Push them forward with the tangent map of F at P, which lands them at F of P. Then evaluate alpha there. The pullback is well behaved in every way you could want. F star of alpha wedge beta equals F star alpha wedge F star beta. Pullbacks compose the other way round, so the pullback of G composed with F is F star composed with G star. And the property that matters most, F star of D alpha equals D of F star alpha. The pullback commutes with the exterior derivative. Now compare with vector fields. Vector fields do not push forward unless F is a diffeomorphism. If 2 points of M land on the same point of N, which one would you use? There is no answer. Forms, on the other hand, always pull back. Naturality is why forms, and not vector fields, change variables painlessly. Naturality is also what makes integration coordinate free next lecture. 2 examples. First, polar coordinates. Careful, the angle here is called theta, which has nothing to do with the tautological one form. Let F send r and the angle to r cosine theta and r sine theta. Pull back dx and you get cosine theta dr minus r sine theta d theta. Pull back dy and you get sine theta dr plus r cosine theta d theta. Now wedge them together. The dr wedge, dr, and d theta wedge, d theta terms both die. The survivors combine because cosine squared plus sine squared is 1. The answer is r times d r wedge d theta. Look at what just happened. The Jacobian factor r emerged from the algebra. Nobody inserted it by hand. Second example. In elasticity, a motion is a map phi from the body into R3. The right Cauchy-Green tensor is literally the pullback of the spatial metric. C equals phi star g. The Lagrangian strain is E equals 1/2 of phi star g minus g. So here is the moral. Any formula in continuum mechanics carrying a stack of partial x by partial x factors is a pullback that has been written out in components. 6 things to take away. 1. The cotangent space is the dual of the tangent space, and its components transform covariantly. Momentum, defined as the partial derivative of the Lagrangian with respect to velocity, obeys that law. So, momentum is a covector, and phase space is T star q. 2. The differential df needs no structure at all. The gradient, which is df sharp, needs a metric. Do not conflate them. 3. T star q carries the tautological one form theta. Theta at alpha q applied to v is the pairing of alpha q with t pi of v, and in coordinates theta equals pi dqi. Then omega equals minus d theta is closed automatically. 4 k-forms are alternating covariant tensors. The space of them has dimension n choose k, and the wedge is graded commutative. 5D is the unique antiderivation extending the differential with d of d equal to 0. On R3, d is grad, curl, and div. 6, f star commutes with d and with wedge. The Jacobian of a change of variables is a pullback. For Lecture 4, read Frankel, sections 2.8 through 2.10, and Chapter 3. That is, orientation, pseudoforms, the interior product, integration, and Stokes' theorem. We finish by writing Maxwell's equations in 2 lines.